One of the most useful tools we can have to measure these things we've been talking about, like current, resistance, voltage, is called a multimeter. Some of these things will also measure properties of diodes, transistors, capacitors. The one we have here is one that we use in the lab sometimes. It's less than $10. Sometimes you can even get them on a giveaway for free. It's important to know how to use one of these. If we want to measure anything except very high currents, we plug the two probes here into these two bottom ports. The one labeled COM, or common, means ground. And then up here, this one is labeled volts and ohms and milliamps. The very top one is for high currents. So just the bottom two is all we're going to need. You can measure resistance by selecting it from this knob, and you touch the probes to the end of the resistor. You measure voltage between 2 points that you touch with the probes. And usually we measure voltage in a circuit with the black probe touching the most negative point in the circuit, our lowest point, our ground. This is kind of like sea level, although sometimes you'll see circuits that have power supplies both above and below what they call ground. We measure voltage across things like batteries and resistors, which means the voltmeter is set up in parallel to the object we're crossing. In the diagram below here, we're measuring the voltage across R2. The V inside a circle is the circuit symbol for a voltmeter. If we look at this circuit before the voltmeter is attached, we know the equivalent resistance here, we just learned about series resistors, is R1 plus R2, so the current must be V1, the battery voltage, divided by R1 plus R2, and therefore the voltage difference from between the ends here is I times R2, or V1 R2 over R1 plus R2. By the way, this is called a voltage divider, and when we use this to make a voltmeter ammeter, we have to keep in mind that we don't want our measuring device to alter the system we're trying to measure. For example, in chemistry, they have great big foot-long thermometers that if you use that to measure the water temperature in a pool, you're not going to change the temperature of the pool by any measurable amount. If instead you took that giant thermometer from the chemistry stockroom, which is usually pretty cold, and tried to measure the temperature of a spoonful of coffee, you're going to get a really wrong answer because that giant cold thermometer is going to completely cool down that tiny amount of coffee. So we're trying to figure out, should the voltmeter here be a high or low resistance device? If it's low, let's say resistance of the voltmeter itself is 10 ohms, and we put it in the circuit above here, and we have a 5 kilo ohm and 9 kilo ohm resistor. What we'll find is R2 and the voltmeter are going to be in parallel. So we've got this 10 ohm resistor and this 5,000 ohm resistor in parallel. They are effectively a resistance of almost exactly 10 ohms. That is in series with R1. So instead of this being 14,000 ohms, now it's going to be like 9,010 ohms. So now what's the voltage across this? 14 volts times this tiny amount, essentially 10 ohms, divided by this. We only get a very tiny voltage across this. So by connecting this low resistance device in parallel, we've completely changed what's going on in the circuit. There's almost no current going through here anymore, almost no voltage dropped across it. It's practically like the R1 is the only thing in the circuit. Now, what we should try instead is, let's say the voltmeter is high resistance. Let's say it's closer to 1,000,000 ohms. Now, it's still in parallel with this 5,000 ohm resistor, but what does the parallel combination of 1,000,000 ohms and 5,000 ohms look like? We know how to do that. We see that it's 4,975 ohms, very close to what it was. Our total resistance, adding this to the 9,000 ohm resistor, brings us to, again, very close to the 14,000 ohms that we had without the voltmeter. And the voltage that we now measure is almost exactly 5 volts. We would have gotten exactly 5 volts with a perfect voltmeter. So this is this is what we want. We want our voltmeter to have high resistance so it doesn't disturb the system. Actual voltmeters will have even larger resistances, maybe more like 10 million ohms. They'll disturb the system even less. What about if we want to measure current? Here we're trying to measure electrons flowing through the circuit, so we have to break the circuit and splice in the ammeter. In other words, we cut this wire and connect the black lead of the voltmeter to one side and the red lead to the other side. The current has to actually flow through the meter. Now, it doesn't make any difference where we put the ammeter in this circuit. Because it's a single one-loop series circuit, the current is exactly the same everywhere, so I can measure it anywhere. Should the ammeter be high or low resistance? Well, the total resistance in the circuit is now going to be R1 plus R2 plus whatever the resistance of the ammeter is. We can see pretty quickly, since this is a series connection, we want this to be as small as possible, so we barely change the number that we got here. What if we do it wrong? What if we hook something up wrong? Well, if we were to connect the voltmeter like this in series, now the total resistance before, which was 14,000 ohms, is now going to go to millions, meaning our current drops to practically zero and the circuit stops doing whatever it was supposed to be doing. We'll essentially figure that one out right away. On the other hand, what if we have the device set as an ammeter, but we connect it across a resistor instead of in series? Now we have a parallel connection. So we've got our 5,000 ohm resistor in parallel with maybe a 5 ohm resistor. It's going to look like we just took the big resistor out and replaced it with a little tiny one, because almost all the current goes through here. In some cases, this can actually break the ammeter. Really, it'll blow a fuse inside the ammeter, depending on how much current is flowing. If you have a $5 or $10 multimeter and you blow the fuse, you've essentially lost that ammeter. It's just not worth it. The ones that we have, unfortunately, when this happens, rather than just stop working, we a lot of times just get garbage from them. So you have to be careful about what voltmeter you buy. Finally, if we're measuring resistance, we don't do this when the circuit's powered. We pick up a resistor and measure it. It's very common for people to measure the resistance of a resistor by pinching the resistor leads onto the multimeter leads with their fingers. So, left hand on one end of the resistor and the black lead of the multimeter, right hand on the other end of the resistor and the red lead of the multimeter. Again, you're really making a parallel circuit path where you want to measure the actual resistance of the resistor, but your body is a parallel path. Typically, your hands are dry, your body's resistance is around a mega ohm. If you're pinching the ends of a 1 kilo ohm resistor, you're going to get maybe 999 ohms, good enough. It's not a big concern for small resistances. Now, if you try and do that same trick with a 2 mega ohm resistor, now we've got the 2 mega ohm resistor in parallel with your body at 1 mega ohm. We get 0.667 mega ohms, which is nowhere near 2 mega ohms.